afternoon. So today we'll start with the fluid dynamic simulation setup in ANSYS CFX. Up to last class, I have shown you how to prepare the model, three-dimensional model, and we have saved those particular model rotating domain separately as well as computational domain separately. Now today I will show you how those particular two files will be used in ANSYS environment, and then how we'll be preparing the mesh, how we'll be preparing the setups, and that's all. Let's see how much time it is required. It is a long exercise. I will try to make it crisp. If I cannot finish within the time, so then I will show you some fast forward video. So and later on, as I promised you earlier, I will give you the notes in PDF format. So first, basically we have done this exercise in ANSYS, basically 2021 R1, and then here this version is 2022 R1. In combination of these two, actually that was the earlier version, now it is the latest version we have. So in your computer, when you will be opening, so you have to open the workbench. So then this type of interface will come. Now, first of all, what you have to do, you have to import the geometry. So here it is geometry. So you drag and drop it here. So whenever you will be drag and drop here, so this type of panel will be opening, and on this particular panel, if you right click on the geometry, then you will get the option to call those particular files which we have already saved it earlier through the SolidWorks. So to call this, basically you can double click on this also. So then a new geometry modeler will be opened. It will be looking like this, another interface. So first one, it is the ANSYS workbench. There are lots of tools available here in this left hand side, and initially this is the toolbox. So and these are the component system. So here we require geometry first, and then we will doing work on the mesh, and then there are some other options, some other more other tools, CFX, all these things we will be using. So right now first we will start with the geometry. So drag and drop it here, and then after that double click on it or right click on open it. So this type of interface it will be opening. Now in this particular interface you can see there are different planes, XY plane, ZX plane, YZ planes, all these planes are defined, and here it is appearing as 0 parts and 0 bodies because we have not called those files whatever we have prepared earlier. So our objective will be to call those particular files. So first thing will be to select a plane. Here we are selecting XY plane. You can click it and then import the external geometry file that we have prepared in the last class. Actually not last class, I have shown you in the last class. So then we will reach that particular location where those particular files were saved. So initially we will start with the rotating domain. So that is why I have selected the rotating domain, and then you can open it. This part 10, this one actually while we are doing the exercise, so that is one residual file we could not, means during taking the snapshot that was remaining there. So this is not that. So rotating domain and computation domain, these two files actually will be using here. So whenever we just call that particular file, after that you have to generate. So this is the place, this is the button, you have to click it here, then it will be generating. So now you can see those particular files whatever we have prepared in the last class in combined formation. In combined formation, if you can remember, there was a cylindrical portion, that fluid domain, as well as solid domain, the rotor, and we use the combined subtract, then we have put it there, and then we saved it. So those particular file now I have called through the geometry tab, and then I have generated it. So now this particular file, it is visible. Now you can see some of the characteristics of this particular geometry whatever it has been shown here. There are two parts, two bodies. It must be there because here I just told you So even if we are calling on single file, but actually there is within this rotating domain there is also rotor. So these two parts, two bodies must be visible. If it is not showing like this, then you have to check your geometry drawing. So then you have to go back to the SolidWorks and you have to check whether the file has been properly saved or not. So you have to work on that particular portion. So here what we have found, that this particular figure, now it is visible in this particular interface. So now what we have to do, whatever exercise we have done in SolidWorks, the similar sort of exercise we have to done, but there we have used combined that particular command. Here there is separate command, this is called boolean. So through this boolean, basically we have to do those same exercise. So you can go to this create button here, and there are several options. So we will be selecting boolean, which will be actually subtract. That means same, this particular geometry design modeler. So this particular modeler had to sense what we have done in the SolidWorks. So similar sense or similar command I need to give it here in order to make it confirm that okay, fine, there are two bodies and one body I have subtracted from the another body. So those things already we have prepared in that manner in the SolidWorks, but I have to make this particular part of the software to sense that the same thing. That means there are two bodies coexist in the same position, and one will be the solid one, another will be the liquid one, and one is basically taking place inside another one having the subtraction mode. So here this command is the boolean. So in the boolean, I have chosen the boolean. Whenever I choose boolean, so this particular option will be appearing, and here different options of the boolean it will be appearing. So there was addition, here it is unite, now subtract, intersect, imprint faces, different option is there. So here we will be going for with the subtract. So we will choose the subtract, and then what will happening, this target body we have to select. So whenever we choose the subtract, so definitely the software will ask subtract of what, from whom. So then target body and tool body, these two option will be appearing with highlight. So you have to choose which one will be the target body, which one will be the body, tool body. So target body will be this fluid domain, that means the cylindrical domain, and this your tool body, that will be your rotor. So you have to select. You can select by choosing the body from the geometry itself, or through this particular part. So here ultimately what will happen, initially this you can keep this target body as a cylinder, just I told you, and the turbine will be the tool body. So you select by clicking here, you select it from here also and put the apply. So whenever you press it apply, so it will recognize those particular bodies. Now your option will be to generate. So generate is this button. You will be pressing this particular button to generate. When it will be generating, so its color will change. So initially it was transparent color, while after recognizing the body you are pressing this generate, so now it will change the color. So now it will be looking like this. After that, what will happen, you can see now it is recognized that it is one part on one body, and there is solid body also exists. So here basically those two bodies, which it has been started as a two part two body, now it has recognized as one part one body. Inside this there is a solid body. So now it is ready for the for next operation. So that now what you have to do, you have to define what is the properties of this particular domain here. So basically this is fluid. So you have to give the option to the fluid. So and once you define this particular body as a fluid, then again after each and every step you have to press the generate. So then it will be recognizing that what is the material of this particular body. Now for the solid body, you go for the Boolean again, and you can already we have gone to the Boolean, and this for this particular body rotating domain, it is actually okay, this has been repeated, this particular slide has been repeated. So the rotating domain, it has been given as the fluid without the turbine, and previous one the actually after generating. Okay, fine. So geometry will be completed once we press the generate, so its color will change and this particular geometry will be completed. Now our next option will be to call the computational domain. So this part of the geometry we have recognized, we have performed the Boolean operation, and we have there was two body two part, and we combined it through the Boolean option, we make it subtract, then we define its material characteristics by fluid, then we generated it now been ready, and it is now inside this particular part. Now this particular portion, that means A, geometry A, it contains those rotating body. Now similar, I have to recognize the other part, that means computation domain. So when we are going for the other part, again you just click, drag and drop. So another this type of panel, it will be appearing here, and then again you can double click or you can right click on it and left click on it, then it will be opening with another interface, similar interface. Now this particular interface B geometry, it has been automatically taken a name B geometry. So this B geometry, now you need to import the stationary domain in this particular panel. So import this computational domain, and this computational domain now you generate. Once you call it, then it will not be visible. Once then you generate, after importing, then once you press the generate, then it will complete the action. So once you generate, click on generate, then you can see, okay, fine. Now all these two will be observing. Now what is this? This is the computation domain, but subtracted with the rotating domain. In this particular manner itself we have prepared it. Previously whatever you have shown, you have seen, that was the rotating domain, inside there was a solid body, rotor. Now here this is the computation domain, inside that particular cavity which has been generated due to the subtraction of the rotating domain. Now this thing will be appearing. Now you have the option, you can go with some wireframe sort of view, you can change the view. But here changing view is not that required, so directly we will go with this particular geometry form. Now again you have to check how many parts, how many bodies. So right now it is observing 2 parts, 2 bodies. So we have to combine these things, and combine operation here we will be doing through Boolean operation. So here what we will be doing, we will be choosing again to create Boolean, and then when we will do it Boolean, so again the next part what will happen, Boolean options, it will ask for Boolean option, which type of option we will perform. So here Boolean option will be subtraction. So whenever I will give the command for subtraction, so what will happen, again it will ask subtract of what from whom. So then it will ask for the target body will be the bigger one, and what is the tool body which we need to subtract. So again you can recognize this body by clicking on it, and then you can apply it. Once you apply, then what will happen, first one I have applied, so one body it will be showing, and then whenever I am selecting second one, so it will be second body. So you will move the cursor here, and it will be highlighting, it will be something differentiating from the surrounding. So now you select it, and then ultimately you will be generating. Once you will generate, so its color will change. So whenever its color will change, you will understand. From here you can check here. Earlier if you see, this was the 2 part 2 bodies here. Now here whenever we are doing this generate option here in this particular part, so what is happening, it is becoming 1 part 1 body. So 1 part 1 body, that means we will understand, okay, our operation is successful. Now we can see it through this wireframe view, so how it will be looking like. So now after that basically what will happen, so far what you have done, we have recognized our rotating part in the geometry. Now we have recognized our computation part in the geometry. Now our option will be to generate the mesh of these particular bodies. So it is a very important part. If you cannot generate your mesh properly, so your operation will fail in later stage. So generating mesh is very much important. So we will take one by one geometry at a time, and then we will perform this meshing. So what we will do, we will take this mesh, again this particular part component system, we will press drag and drop here. So at a time better if you choose one mesh, you drop it here, and then we will connect with this particular mesh. It will looking like this. Now you can rename this particular mesh, say you can rename the mesh rotating, this very short name, and that particular name should be compatible with the program also. You cannot use, there are some rules, you cannot use some special character to give the rename sort of thing. So you have to check, so you have to give the name here, and then you have to connect which geometry's mesh I would like to do. So how do you collect? You have to connect this particular geometry with this mesh. So next stage will be the connecting. So connecting will be again you press and drag and drop. So you press, drag and drop it here. So there is not as such a rule for provision of putting this particular mesh here itself. You can bring and drag it here also, and then you can join it from here to here also. But in general we keep this particular component side by side, so there should not be any confusion. So this is only for observing all these things. So we are basically drag and drop this geometry A to this here. Now what happened, you can see. So suddenly whenever I have made one component, I have bring it here, so automatically this geometry which was earlier B, so it has taken a name as C. So in that sense, so automatically that has been updated. So from A to B, now this B initially, if you see, initially it was B. Now once I bring it here, so it has been changed the name automatically as C, but those particular properties are remaining here. So now it has been renamed as B automatically. So I will join these two here. Now after joining, I can double click on this, so this particular interface will be opening. This is the platform for giving the characteristics of the mesh. And since I have connected the geometry to this particular mesh component, so now those particular geometry which I have connected with this particular platform, that will be observing. So here you can see, and every time basically you should check that whether your geometry is properly imported here or not, it is properly visible or not. So how to do this? You have the geometry, this is the plus sign, you can click it here, it will extend, it will form a tree, and there will be components, and you can press it, those part will be highlighted. In this manner you can see, you can check the properties of this particular components also, whether whatever characteristics we have given in the earlier stage, whether that has been properly conveyed or communicated and came here or not. So all these things you should check. So here I have not shown you in those details because we have some other purpose. Here after checking all these things, now we will proceed. So first thing will be, so here you see there is the coordinate system automatically taken from the geometry. Now this mesh will be appearing. Now I will provide the different methods of the meshing. Which method I will apply to form the mesh, which type of mesh I will apply. So those things I have to define it here. So for this, what I have done, I have right click on this, and after right clicking I am inserting the methods. So when I am inserting the methods, so what will happen? So automatic method will come. Now the automatic method, now I will edit this particular method. So automatic method I have selected, and now the geometry with which the mesh will be generated, that I have to select. So first thing is, whenever I have selected this automatic method, now here geometry section, there is shown no selection. That means right now I have the geometry that is there. But here whenever geometry came, so I have to recognize again that which geometry I would like to make a mesh. So those options already you have understood. You can click it here, so it will be open. And then initially what I have done, so first thing will be I have chosen this particular part of this. So by clicking the rotating domain, I have selected it here, and then you have options here. Here, if you this method corresponding to the method, there are options. So here I have, if you click it here, there will be four options will be coming. So here I have selected 4-5 option will be coming. I have selected tetrahedron. Tetrahedron type of mesh I will be selecting. There are different, and tetrahedral patch conforming type of method. So here you can see I have listed down different type of meshing methods and the description of these meshing methods and when to select. So for our case, we have complex geometry. Already you have understood the way we have made the geometry. So here I have give the importance to this particular part, that high quality mesh I require and clean mesh I require. And obviously my geometry is not like simple rectangle sort of thing or maybe plate sort of thing. It is a complex geometry. We have put so many angles and so many curvature here. So that is why we have selected this tetrahedron, which is coming under the patch conforming method. So there are different other methods, 4, 5, 6 methods are there. So again we are doing it for the 3-dimensional. So we are selecting for 2-dimensional geometries. There are different other options are there. You can see the tetrahedron sort of mesh here, prism type of mesh is the arbitrary polygon. Each and every type of mesh, they have some advantage as well as some disadvantage. So accordingly you can select as per your, and obviously which type of mesh you will be selecting, that will provide you the accuracy as well, how many number of mesh, how many number of element it will form to discretize those particular bigger, to discretize those geometry. So it will create a number of the elements. So you need to calculate the different points corresponding to this element. So the time required to analyze or calculate all these things, it will also have some factor, as well as whether that type of capacity is available with your machine or not, that is also another factor. So accordingly you can select which type of mesh you will be selecting. Okay, so now here, so meshing, in the meshing, now you have to select what will be the physics of the preference. So physics preference here, different type of physics preferences here available. Mechanical, non-linear, mechanical, electromagnetic, CFD, will be selecting the CFD. Again, then your solver preference. Solver preference, you have fluent, you have CFX, polyflow, standard. Many people option fluent, and here we have selected CFX. Our purpose was of this exercise was to show you some setups of CFX, because this is better to handle the steady state as well as transient phenomenon. In our case, that is the transient phenomenon. So how this CFX setup can be used for to solve this type of problem, that we are trying to show you here. So we have selected the solver preference as CFX, and then element order, there are different type of element order, quadratic, linear, program controlled. So basically for complex geometry, a better performance, we selected as the quadratic sort of element order. As well as now what we have to do, we have to recognize the faces of our geometry, different face. So this is our rotating domain. In this rotating domain, so if you can see fluid will be coming and entering into this particular part, and it will be going out. And this particular rotating domain, it is interacting with the competition domain. So there are different parts of this particular geometry. So one will be the inlet, another will be the outlet, another will be the part which is basically interacting with the competition domain. Again there are something which is inside. So all the faces I need to recognize. So those recognition, to do those recognition, you have to select this face button. So once you select the face button, then you start recognizing those parts. So what will first we choose to select the inlet to this particular rotating domain. So you will click on it. It will be highlighted like this. So after highlighting, or you can right click on this, you can rename it, because whenever you will be selecting here, So it will take some automatic name. So better to rename it so that in later stages we can call as per the name. And obviously you should note down the name whatever you have provided during this operation. So here we will first give the name, and name coding will be as per your wish. How you would like to define those particular name and which stages, because you can see the similar type of object will be just like this. This is a rotating domain. So here this is inlet is there. When we will be talking about the computation domain, similar part which is placed here but is a part of computation domain, same type of feature will come. So I have to give name to this part also, interface. So those naming should be such so that you can understand, and you should actually take a note of this. So anyway, so when we are giving the name, so what will happen? So you can give the name just here, inlet. This is I have made the short form. This is basically rotating domain and inlet. So I have given name like this. Now I have to now give the name to the outlet. So inlet I have given. Now I can select the outlet. Now sometimes it may happen that while you are selecting the inlet, so orientation of your figure will be such. So when you are trying to find out some other face, so you need to rotate that. So then you have to select, you can press the button of your mouse and you can just tilt it so that you can find the another part. So accordingly you can choose the other part. So those rotation, internal rotation of this particular figure, that you can do using this as per the setting of your computer. You can middle button you can press, or left button you can press. You can check which type of setting is available in your computer, and you can tilt this particular figure and you can choose the proper face. So after selecting this particular face, again we will give the name. So create a name selection, and then we will give the out, shout out. So basically this is the rotating part out. So now we have to provide the face of this particular wall of this rotating domain, which will be actually interacting with the computation domain later. So for wall, basically by observing itself, if you see it here, so here is one white line. So basically this full curvature, this has been divided in two parts. When it is being generated, so although it is a part of the cylinder, but when you will be bringing your cursor, try to select it, you will find that half of the part will be selected and half of the part will remain be there. So you can basically press Ctrl and left click to select multiple sort of face. That will be applicable for other case also. So if one single click, that will give the selection of a single face. So multiple face if you would like to select, so you have to use the control and left click, and you have to otherwise you can check also in which way in your computer that particular setting is there. So after that we will give the name. So name selection, then again this is I have given name as per my wish. So it will make me understand that I am talking about those particular parts which is actually interacting with the your computation domain in the wall. So now what will happen? Now we are going to select the inside material. So inside material, that means the rotor which is inside this particular rotating domain. That also I need to select. That is also will be interacting with the fluid. So for this, basically that is a combined body which we have defined earlier in earlier stage in earlier other software, that means SolidWorks CAD software. So it will be considered. So for this type of selection will not be possible. So far we have done. So we are selecting the box effect. So here what will happen when I will be selecting the box effect? So this particular will be vanished. So now you can select this particular turbine. So different tools for selection are there. You can play with these tools and you will understand then using which tool you will be able to select which type of geometry. So ultimately whenever I select this one, now what will happen? Now my next one will be to give the name. So now I will give the name. Again here I have given the name as a rotor. Once I give the name as a rotor, so now here all the things whatever we have given the name, that will come under the name selection. So this name selection, it is coming under the mesh. So name selection, so this is the in, this is the rotating domain in, this is the rotating domain out, this is the rotating domain wall, combined wall, half combined wall, and this is the rotor. So 4 part. So actually rotor, and it's covering all the faces. So this has been prepared. Now we'll see how this particular part will be used later. Now what will happen? So since there is a solid part, solid body, that means the rotor is there. So I had to, and this rotor is actually having a complex geometry, very complex geometry. So I have to provide certain option of producing very finer mesh and with this curvature, so that it can calculate the fluid characteristics surrounding the solid body. So I have to give inflation layer surrounding the solid body. So this inflation layer option I have to give. So inflation layer option will be provided over this particular solid body itself. So insert, so right click on this particular mesh, insert inflation. Inflation, you see, if you see this particular figure, you can see this yellow one, I am assuming yellow one, this is the solid body and their fluid is traveling, and I am creating multiple layers. So basically this multiple layer will be creating the very fine tuning calculation, and this particular provision I need to give it specially to this particular geometry, as well as I will give it to the competition domain when I will be representing a solid surface, channel surface to the competition domain. In that particular part I will give it later. Right now I am giving it to this particular rotor. So here now what you have to do, you have to give some of the information, details of the inflation. So details of the inflation, while I have only simply given that under this particular mesh exercise I have to give the inflation. So now I have to define in which body basically I would like to give the inflation. I have told you already, but here I have to recognize the software that what is the body. So basically, so you have to select this, and boundary, that is the no selection, it is told as node selection. And maximum layer, growth rate, these are the properties, transition ratio, these are the properties which has been taken as a default. So this particular value also you can change as per the calculation. There are certain calculation for calculating the inflation layer thickness and what will be the inflation values. I will show you later. So here first thing will be the geometry selection. So geometry selection, here what you can do, so geometry selection, named selection. So here already we have given certain names, so we will be selecting the name selection. So in the name selection, then once I select name selection, what will happen? I have just now created these 4, 1, 2, 3, 4, in, out, and this surrounding wall and the rotor. Now this thing will come. That is the reason I have created these things separately, so that if required I can call those parts separately. Otherwise, if I could have defined all these things together, it was difficult for me to define some fluid flow phenomenon surrounding those parts. So the value we would have got, either that was erroneous or this particular value will not be computing the actual scenario what is happening surrounding this particular part. So here we will be selecting the rotor, that particular geometry, and then we will be providing the information about the inflation. So information about the inflation, that means which type of information is required for the inflation layer. There are 4, 5 options are there. First, in layer thickness, smooth transition, first aspect ratio, last aspect ratio. You can go with any one of the option. Here I have chosen the first layer information, first layer thickness. So first layer thickness I have calculated because there are some tools which is available in the internet. Means there are some logic also, but here I would like to tell you there are some tools available in the internet. I have shown you the links. So that particular tool you can calculate what may be the particular thickness of this particular first layer thickness. So by putting the value of your geometry. So you can do this calculation separately and you can choose the values, you can put it here. So here, and you should remember one thing, that the y plus value will be less than 1.0 for our case. I will show you there are different regime of y plus value. Y plus value means that inflation there. So that particular different regime. So here different options are given. So y plus value, it will be basically less than 1 while we are selecting the turbulent model of the calculation k omega SST. In our case we have used k omega SST because again I will show you different options are there. So that k omega SST we have considered because we have the complex geometry. Now if you are selecting k epsilon model for the turbulent model, and then you have to select your y plus value in between 30 to 300. So researchers has already given certain criteria. They have tested this y plus value and they have published some data that for which condition you will be selecting which type of y plus value. For our case, we have to select the y plus value that should be less than 1.0. So there are calculation techniques. If you go in this particular website, so already I will give you the this particular link. So here, what is written here? What will be the free stream velocity? What will be the water density? What will be the water viscosity at 25 degrees Celsius? Characteristics length of the rotor, and what will be the desired length? Desired length, I told you, I desire my y plus should be 1, less than 1. I have written it 1. So what will be the theoretical y? That means thickness. So and what will be the Reynolds number corresponding to this value? All these things you can check. And here in my case, the exercise I have shown you, I have assumed that in my channel there will be linear velocity of the fluid of 1 meter per second. So when linear velocity is of 1 meter per second and my water density corresponding to 25 degrees Celsius, my fluid density it is 998. If it was air, its velocity will be something different. If my fluid stream velocity it is something different, I had to give some other value. If it was air, in general we do not consider that much lesser amount of the velocity for the air. Wind turbine, say suppose we are trying to do the exercise for the wind turbine, same model I am doing for the wind turbine. I will change the topic, I will change the fluid medium characteristics. So instead of when we dealing with the wind turbine, what will happen? This free stream velocity I will consider more. It may be 50 meter per second instead of 1. This water density it will be less. Water density and not water density, air density, and air viscosity will be something different. And characteristics length of the rotor, that will be same in that case, because if we would like that this particular rotor will be running under the wind condition. So that particular characteristics length I would have taken here. So characteristics length of this rotor, that means we are talking about the diameter of this particular rotor. Now desired y plus, then I would have taken here 1. Then this particular calculated y, it would have been something different. So two cases with two medium I can get different value. As well as there are few other things that you can cross check what will be the, if you are considering this type of value, so how you will be getting the two nodes distance. So all these things you can cross check through the geometry. But here we are not diverting our topic. So we are coming back to our topic. So this link is there. Using this link you can do the exercise. So we are coming back here. Here we have considered first layer height. We have calculated that will be approx 0.02. There are, see, this is not straightforward. There are some other criteria also selecting this first layer thickness. That will give you the exercise I have shown you in the last page. That will give you an idea. But there are few tests also. Through this particular test I can fine tuning that also. I will tell you later. So normally I assume here that this is 0.02 millimeter should be the first layer height, and maximum layer I have assumed as 12. Growth rate I have assumed as 1.2, and then I press the generate. So after that what will happen? After that its value will be changing, its color will be changing, and finally after completion of this mesh generation, it will take some time. So after, and in the meantime, if it encounters some error, so it will give you the error message here in this particular part of this during that particular time. So if your this creating this particular mesh itself is the biggest step towards the solution. So if you cannot create the mesh, it will be difficult for you to further proceed. So when I just told you that y plus value, what will be the y plus value, what will be the first layer thickness, that hint we can get through this particular tool which is given in that particular website. There are similar other tools also available in the internet. You can write down y plus value calculation. You may find different tools available in the internet, freely available. So I have shown you only one option. So before proceeding, what you have to do some grid independence test. Grid independent test, actually what happens, so suppose I have prepared this mesh successfully, then I will proceed, I will complete the exercise, and I will get the power value, torque value. That is my ultimate desire. So using that, I will calculate the coefficient of the performance or coefficient of the torque. So basically, corresponding to how many number of element it has been generated here, corresponding this thing, if I am getting certain coefficient of performance value, or maybe some power value, or maybe torque value, so that if I consider as my output, and then I keep on changing this mesh value, so then if it give me the consistent result, then I can say, okay, fine, the mesh I have created, that is giving me, that will give me the consistent output. So then only I should proceed with those particular parameters of the mesh. So that exercise is called grid independence test. I will show you later stage. But if this grid independent test, it doesn't support your mesh, what right now we have provided it here. So I have to modify this mesh value again here, all these things, whatever we have done. So it is a multi-layer checking. So here say whatever value I have given it here, that will work, and now I will proceed. So here you can see first layer thickness. This is actually another screenshot. It is looking like 0.003, 12 and 1.2. So and now if it prepare it successfully, so it will be looking like this. You can see the meshes are non-uniform sort of thing. That means here is the curvature part, this is the rotor part here, and here is the rotating domain. So rotor is having a complex geometry. So we have created inflation layer here. So the mesh is created here surrounding this particular part. It is so dense. So it will capture all the phenomenon of the fluid which will be gliding over this particular blade. So the mesh has been considered in this manner so that it can arrest all the information which is available in the fluid. So this was our actual purpose of giving the inflation layer. So we assume that particular value we have assigned it here, that will work and that will pass through the GIT test also. So we assume it that. Then we proceed, because GIT test only you can perform only after getting the final result. So at this stage we are assuming that this value we have considered, that will okay, and then we complete the exercise, and then if something is wrong, we have to come back to this particular part and we have to adjust the value. Then you have to again check and again justify. So that is the reason I told you that it will require lots of time. Not possible to deliver this lecture within 1 or 2 hours. So it requires even sometimes a week to prepare this setup. So that is the reason I have decided to make it some preloaded case. So this type of presentation I have prepared. So it was not suitable to deliver the lecture within 1 hour time. So now, okay, fine. We are now going ahead. So after forming the mesh, the mesh has been formed. You can see patch conforming method, it is shown, the tetrahedral. The inflation layer, that is also we have prepared. All the name of the selection, that has been prepared, and now this is appearing as this. So, and some warning messages are also there. So this warning message also you can, if warning message is such that you cannot proceed further, so you have to try to debug those warning message, and after solving this only you can proceed forward, or otherwise you have to adjust these values and then you have to regenerate again and you have to cross check. So let's say this will work. So we are now proceeding for the next part. So just I told you, so if you require something, some editing, so you adopt the modification and you proceed. You can change the type of the mesh, you can change the thickness, first layer thickness, and then you can proceed. Fine. So what will happen now at this particular stage? I just told you we require GIT test, grid independence test. So grid independence test, basically we try to find out what is the final output corresponding to number of the node or number of element generated through this mesh. So how to find out those, how to get those information? Those information you can get through this statistics. Here it is showing us almost 2 lakhs amount of the, less than 2 lakh mesh has been generated, element will be 94,000, almost 1 lakh. This is not ideal. I have prepared this particular model to show you the example. This is not ideal for actual exercise. In actual exercise, it should be more than 50-60 lakh, and it will require that much amount of the time based on your capacity of your computer. It may require 1 day, minimum 1 day. Minimum 1 day is required, more than that, to run the exercise, one run, and then you will get to know whether this is successful or not. Then again you have to come back and you have to do. So it is a very lengthy process. So anyway, so for to showing you this exercise, I have taken some coarse mesh, and values are also limited. So now, so suppose now if I press the generate at this particular stage, so what will happen now? It is basically creating finally. So now after mesh generation, it will be looking like this, and it will be looking like this. Okay, fine. So one slide, most probably it has been jumped earlier. Actually, this slide should be after this mesh generation. So it has been changed actually. Anyway, so now rotating domain, that mesh generation I have performed. Now similarly I have to perform the mesh generation for the computation domain. So similarly, similar operation I will do. I will drag a mesh component here and drop it here, and I will make a connection with the geometry of the computation domain to this particular thing. So I will do this exercise here. So similarly, I will I will try to import this particular figure, and then I will generate. Then only it will be visible, and whenever it will be visible, I have to select the physics preference. It is CFD, and then I have to give the solver preference. It is CFX. Then I have to give the element order. It will be quadratic. Then I have to go for the outline, and this outline will actually give you the automatic. So this automatic, basically I have to select those faces. After generation, it will be looking like this, and then I will be giving the tetrahedron mesh. Different type of mesh was there. So tetrahedron mesh I have given. So because we have given the tetrahedron to the rotating domain, so we have given this tetrahedron mesh for this particular computation domain also. Now after that, what will happen? Basically, already you have understood, we have discussed last class also. The length of the rotating domain and the size of the rotating domain, it was a bit of smaller comparative to the computation domain. So basically the mesh size of the mesh it will be generating in the computation domain, you can change, alter, because ultimately if you, the value you are putting, mesh size you are putting for the rotational domain and maybe very near to this rotor, it is very less. So now if you apply the same thing in computation domain also, then it will take lots of time. So you can adjust here the size, but depends on those things that you have to go through the GIT test. So your output should be consistent. Accordingly, you can change. After doing some preliminary exercise a few times, then you will understand for your particular setup which type of data are actually suitable for computation domain as well as the rotating domain. So not a first time you will get the idea ki your value will be this particular value is suitable for the rotating domain and that particular value is suitable for the computation domain. So you have to perform several exercises, then only you can tune the value, because in this particular sort exercise you are not going to calculate only single value, you have to calculate multiple number of value, and accordingly you have to show you the performance. If you can remember the performance curve with different TSR, you will be calculating different CP value, then only you will be able to produce a performance curve, and that particular performance curve will be corresponding to a particular river flow condition. Now if you change your river flow condition, that means the same sets will be for different other condition. Now if you modify the river construction, so some changes in the river geometry, then again you have to, so you change your all these exercises. So you can consider, say suppose in your performance curve, if you are considering, say I will take 10 points to prepare CP versus TSR curve. So that particular 10 points for a one river flow condition, that means say velocity will be equal to 1. So if you want to find out the at velocity 1.5 what will be the river flow what will be the different values. So 10 multiplied by say you have 5 velocity, 10 multiplied by 5, that much exercise you have to do. Again suppose some other condition has been changed, so that particular change is something, so you have to multiply that, so it will be increased multiple order. So this type of exercise, it will not a single exercise, so you have to do the multiple exercise. So initial level you have to do you have to perform some exercise, and then you will be able to find out what will be which type of value are suitable for your setup. Anyway, we come back here. So since the size of this computation domain and size of this your rotating domain, that is something different, so what will happen, so we have to go for some sizing definition. So I will insert sizing and this element size. So element size, here we can provide the element size. So here we have given element 20 millimeter, and then we have seen this particular value as a wireframe view, and now we will be selecting for a face, as just like the faces we have seen it here at the inlet of the rotating domain, we have selected the face. So similarly we will be selecting those face also. So we will be selecting the face, and in this particular case, first this is inlet to the computation domain. So I will be selecting inlet to the computation domain, similar manner. You give the name, just here I have given inlet, and then I have selected the outlet. I will be giving is the name as an outlet. So you can see here I am giving inlet outlet. In case of the rotating domain, I have used some stroud SH, and then I use in. So it is completely up to you which type of name we would like to give. This up to you. So here, and then again I am surrounding this particular part. So that part I have given, that is the wall part, and then what we will do, I will be basically defining the rotating domain subtracted part, and then this particular computational domain will be visible. Now rest of the part is to show you this part which is inside this particular part, computation domain. So this face also you have to recognize. So first you can see this is the inlet part, that means this particular part it has been selected here similar way, and now this has been selected the outlet part, but this part actually belong to computation domain, this part is not belong to the rotation domain. So rotation domain part already we have selected, but the same position there is some interface, so similar type of part exists also in case of the computation, so we are talking about that part. So this one also there, and then this particular part and rest of the part you can select by pressing Ctrl and left click, and during that time I just told you, you have to rotate your figure, so that suppose if your face is like this, you will be able to select this one, but how to select the back side. So accordingly you have to select, you have to adjust. So that will be the control of your mouse, you will be doing it. So doing that, basically after doing all these things, so ultimately what will happen, you can see name selection, body sizing already we have done, we are doing it for the mesh, and this is actually for demeshing. So initially we have started with the geometry A, then we have created geometry B, then we have put mesh. Mesh suddenly took the name B and geometry B renamed as C. Now here we have put mesh for corresponding to C, it has named as the D. So whatever we are doing, it is for D. That means corresponding to the computational domain. Similar type of name selection that exists in B, which is basically related to the rotational domain. Already we have given the name. So this name already you can see it here. So now what will happen? Now basically a few information is provided here. First layer thickness. So first layer thickness we have to give. So first layer thickness here, similar type of exercise we can do for the first layer thickness of this your computation domain. In this particular case, characteristics length will be changed. Characteristics length initially we have considered for the length of the rotor, and here we will be considering length of the total channel, because channel I would like to show. If this channel length is 2 meter, suppose I am trying to do it almost, we have considered is 2 meter or maybe 2.5 meter in the geometry. Whatever value we have considered, that particular value we have to put it here, and accordingly that value, your y value, that value will be changing, and our target value should be 1.0. Y plus value should be 1 plus 0. That is exist here also. But now the target value will be something changing, and that particular value we have to put it here. So first layer height here we have selected here 0.2, and maximum layer, and this is different than the previous one. So this is 0.2, maximum layer is 12, and growth rate is 1.2. So here after generating, actually you have to press the generate, so it will be, color will be changing, and finally it will be generating like this. And once it will be generating like this, basically it means that some warning is there. Sometimes after doing this exercise you will understand which warning you can skip. So now this warning right now I can skip, and now I can proceed. Even if you are trying to proceed, if it doesn't allow, then only you have to solve the warning which is appearing here in this pop-up, in this particular pop-up. It is allowed, then you can proceed. So now this first layer thickness, it has been increased, and then if required, so you can do the updatation. Just I told you, if something is not supporting, so you can do updatation like this, mesh. Suppose I need to update the mesh. So I will be right click on it, and then updatation, through the updatation we can do. So after that, say finally again, if you are doing any update, so you have to generate again. So now we are generating, and ultimately it will be changing. So whenever it will be changing, finally it is giving you this type of mesh. But this mesh, it is appearing as very dense, that means very small and dense. But corresponding to the rotation domain that I have shown you the zoomed view, so you cannot come to a conclusion that this particular mesh size is less. So maybe it may be bigger than that one. So anyway, so here basically you can see number of node has coming out as 21 lakh, and number of nodes which was there in the rotational domain, that was around 2 lakhs, and then also I told you 2 lakhs is not sufficient. Similarly this is also not sufficient. So and this element, number of element, it has come out as 15 lakh, and it was less than 1 lakh in case of the rotational domain. Again I am telling you, these particular values are not suitable, means you have to adjust it through GIT test and all these things. So the values you will be selecting, so then accordingly you will be densing the, you will be selecting the parameter, you will be tuning the parameter, more number of the element, more number of the nodes will be generated, which will give you the better result. So this will be the actually feature of the GIT test. In this particular GIT test, you can see how we represent GIT test. So basically refinement level 1, 2, 3, 4, 5. Refinement level 1 means I have changed the characteristics of the mesh. So that is the refinement level. So suppose initially whatever I have prepared, that is, I can consider that is refinement level 0 or 1. After and at this particular 0 or 1, so how many number of node is there, how many number of element is there, and this is for rotating domain only, this part. And then with this same characteristics, if I would like to proceed, suppose the characteristics of the mesh we have considered for the rotor, the similar characteristics we have considered for the stationary domain or computational domain. So if this is so, so corresponding to refinement level 1, so I am representing rotating domain values as well as stationary domain values, and corresponding to this I am trying to calculate. So I will get the power, I will get the torque, and from this I can calculate the CP. That means coefficient of power. Coefficient of power is, that means the power which is being generated by this software, that I will consider as a shaft power which is actually being received or measured in case of the actual condition. Here I cannot measure it, here I am basically generating through the software. So if I consider that is the shaft power, and what is the available power in the channel. So available power in the channel, that means half rho A V cube. So that is the available power or theoretical power which is present in the channel. So that V, that will be the channel value, channel fluid flow velocity. A is the cross section area, जो rectangle, that rectangle we have prepared, that is the cross section area, and the V cube, rho is the density, rho A V cube. So that is the this A will be the area of the rotor, and this rho is the density and V is the velocity. So that will be the theoretical power available in the channel. So corresponding to that will be in the denominator, and numerator you will be putting the value which is coming out of the software. So you will get a coefficient of power. So similarly you will get coefficient of torque also. So now this coefficient of power and coefficient of torque, you are getting average Y plus value. So this Y plus value, whatever you are getting out of this exercise, so you can put it here. Now this is one refinement level, and then you will be doing, after adjusting number of the mesh, then you will perform this and you will be getting this type of value. Third one, fourth one, fifth one, everything we can put it here. We can make a plot, and then you can see at which level basically your CP value is not changing. You can see here after fifth level and sixth level, even if I have changed, see here number of load from 57 to 68 lakh, almost more than 11 lakh I have increased, but its coefficient has not been increased. So that means I can fix this particular analysis up to for particular geometry. For this geometry, I can fix that this may be the value, or this may be the mesh size value which is suitable to give you a consistent result. Now I will change the condition. My elements are fixed. Now I will change the condition. Rotation will be, turbine rotation will be more, inflow velocity will be something, and now I will go for, and I can say the result which is coming out, that is consistent. So by observing itself, you can find, you can fix the refinement level. Even if for this particular case you can go with the fourth level also. There is not third digit after decimal, actually it is being changed. So that also you can change. So anyway, so we can have a break. Okay. So we were here. Okay. Now, so our geometry setup is complete, meshing also complete. Now we have to define the our solver setup, CFX setup. So this particular CFX setup, for this you have to bring the CFX setup from here to here. And now in the CFX setup, both the part will be interacting. So okay, fine. So that I have prepared in the next slide. Anyway, I have forgot. So I will show you I will show you one video of this. How it is actually looking like. So you can see I have made it fast forward. So you can see how all the total exercise we have done. Actually we have splitted this particular videos. We have taken a splitted video, then we have edited it, combine it and make it 10 times faster to accommodate all these things. So it was not one time exercise. So we prepare it time to time after completion of one stage. And then I just wanted to show you because I would not be able to show you on live. So a glimpse of live, how it will be looking like. So in this manner you can actually tilt the figure. So in this manner you have to tilt the figure in order to find out your desired faces, and then you will be able to select the face. So in this manner you can put the values, different values. So this is for rotating domain. So you can see the names selections, input to the rotating domain, output from the rotating domain, and the wall part, rotor part. So after creation of this mesh, how it will be looking like. So how each and every part will look like. I just told you, so you have the selected name, you can trace it here and that will be highlighted. You can see which type of options you have selected here, and accordingly if you wish you can change it and you can generate it again, regenerate it. So this type of error will be there, you can move this error. So now again, so this is for computational domain. So in this manner you can select those part which are actually subtracted from the computational domain, rotating domain part subtracted from the computational domain. Those faces actually, interface. So after that we will be going for the CFX setup. So CFX setup, we'll start with this mesh. Now, just 1 second. Now, this CFX, you can drag and drop it here. Now you can give name, or automatically it will change its name. A, B, C, initially C was there, D was there, now it has become C, so it will be D and E sort of thing. So you actually drag and drop the mesh which has been generated in rotating domain and as well as computation domain, and you can put it here. So CFX will consider both the meshes which has been generated now earlier. So now you can actually here I have shown it edit, but you can double click it, so setup will be opened. So after opening this type of interface will come, and now your objective will be to find out to start the setup. So initially geometry is not appearing. So basically after clicking this particular this pop-up, yes, then it will appear. So after appearing this, you will see the characteristics of the geometry that will be shown in the left side, this tree. So here what are the things? So here you can see this flow analysis and this solver, then interfaces, and then expression. These are the parts we will be basically using to develop or to define the setup of this particular CFX. So now here first thing will be flow analysis 1. So flow analysis 1, first thing is analysis type. You can click on it, and then this analysis type, it will be opened. When this analysis type will be opened, there are few options: steady state, transient blade row. While we are dealing with this type of complex geometry for the transient phenomenon, so then we select the transient blade row. This particular analysis type we select. So transient blade row, here we will be selecting mostly for the turbo machines case. Otherwise there are transient phenomenon, steady state phenomenon, that will be based on the problem, your problem. So now we will be applying an OK. So during this time you can see there are different sort of error which will be visible. So you will be defining the setups. Initially this is the default setup, corresponding to the default setup, corresponding to the geometry and mesh you have supplied it here. So you are objecting something. There are several things it is objecting. Time to time we will be selecting few values, and at the end of this CFX, all these errors it should remove. So then only you will understand that you have properly you have selected the options properly, and finally you can compute the result. So anyway, we will go ahead. So after okay, we go ahead. And then you can go for the edit. The first thing will be the, after doing this apply and OK, this message will appear, and the name is the default domain. This default domain you can rename, because renaming is required because you need to recognize it later. That particular domain is for what? Otherwise, whenever you need to select those options in some other option, under some other option, it will be difficult for you to select those options. So better to give the name. So here basically first thing will be the rotating domain, then we will select the rotating domain. Initially we will be doing the setup for the rotating domain. So default setup, I am giving the name as the rotating domain, then I will select under this rotating domain whatever property will be coming, and then I will select it and select the geometry, then it will be okay for that. So rotating domain, so first thing is the rotating domain, and the property name you have to give. So this thing basically, if you see the basic setting, once you click the rotating domain, and then you will get this basic setting, fluid models and initialization. There you will find two options is appearing. So you can select any one of these options, and accordingly these things will be highlighted here. So which part you would like to mention, so you can select through this particular option. Say here I have selected first one, and then fluid particle defined, so fluid 1, and then rest of the other things here, material property, all these things you have to change. Reference pressure 1 atmosphere, here it is here, and it will be change it later. So now what will happen, this air it will be converting into the water. Initially it was here, the environment was here, and I have to change it, just I told you. So I have selected this, fluid has come, by default air is coming, and now I have to change the options. So that is why I told you there are several options, several errors will be appearing. Whenever you are going to select, slowly you will be going to select the correct option, and slowly some of the errors it will be eliminating, and at the end all the errors should be eliminating. So now your water, you have selected the water. Now domain motion, this particular motion it will be rotating. So domain motion, either it will be stationary, it will be rotating. Stationary is for the computation, it is rotating, we are going for the rotational domain. So I have selected it as a rotating. So what will happen after that rotating, and with which unit, you need to define the unit. Otherwise while we will be selecting a particular value, if you cannot connect with the units, it will give you the wrong result, or you may end up with some wrong calculation. During the computation it can create the problem, even if you are selecting correct options, but while it will be calculating, because whatever we are observing, although these are all visual, just we are observing the mesh, but the things is that the values corresponding to the mesh, that is being calculated through the programming inside the software. So whatever value we are giving as an input, that must have proper impact on this calculation. So here I have selected revolution per minute. So revolution per minute, and then we have selected global X. X is this direction. You can see in which direction your axis is aligning. So here X is the direction where fluid is coming in this side, inlet, and it is going out. So fluid is moving in the X direction. So accordingly I am selecting the global X here. Now after that we will be selecting the apply, and then OK. So after that it will be fixed. So now next is the fluid model. Basic setting we have completed. Now here is the fluid model. In the fluid model there are few options. In this particular options, basically whether there is any heat transfer in this particular part. In our this hydrokinetic turbine, there is no involvement of the fluid. Fluid change is not important here. Even if there may be temperature change in the flowing fluid, but that is not going to impact on the power projection. So here this mass transfer is not of our importance, interest. So here we will be selecting as the none, no heat transfer. So in case of your other problem, you can select for the mass transfer, then corresponding option will be arising, and accordingly you have to select those things. But here it is none. So after that what will happen, I have told you earlier, we are going to use SST K omega. So this SST turbulence model, that we need to select. So this basically SST, then K epsilon, K omega, BSL and Reynolds stress, SSG, Reynolds stress, there are different options. For our case, since we are dealing with the turbo machines, complex geometry as well as transient phenomenon, so here we will be selecting this SST model. In normal case, sometimes what happens, when we communicate our findings to any journal, so then reviewers also sometimes ask why you are selecting SST based on the findings which has been done by some other people for their own problem. So you please show us with all the options and give us a comparative chart and prove that this particular SST option, it is giving you the better result. So if I have the experimental facility and I have the graphs which are coming out of the experimental analysis, I had to verify or validate the curve which one is giving me the very closer result with the experimental one, whether it is K epsilon, K omega, SST. So this type of exercise separately you can do. That is the reason I told you that this particular exercise, it requires time, and not a first time or a single go you will be getting the result. So you have to adjust lots of things in order to fix your setup for your particular problem. So anyway, here I am selecting, this is the recognized one, so turbulence model is SST. So once turbulence model is SST, that means shear stress transport. So there are some other option. What will be the wall function? Wall function will be automatic and then apply. So this wall function automatic we have selected, there are also another option. So automatic will solve the purpose, there are few other options also. So you can go on and select those options and you can check. Before that you have to go through the literature, the other option means what. So here we have selected this automatic and transient turbulence, fully turbulent. Transient, you have to check the transient turbulent and this is fully turbulent because the fluid flow which is passing through, it is a fully turbulent flow. There is no trace of the laminar flow, fully turbulent, as well as this rotor will also be rotating. So now then we will proceed, now apply boundary initialization. So we have to provide some boundary condition. So boundary condition, so domain installation, so this box you have to check, and or otherwise you can expand these particular options through this plus by pressing the plus. So after that what will happen? So you can find out it is stationary and rotating. So obviously we will be selecting the rotating, and then coordinate frame. So coordinate, here we have selected coordinate 0, and then the velocity type, the velocity will be providing as the Cartesian velocity, because here we will be giving the velocity in the x direction. So either fluid will be passing x direction or maybe y direction as well as z direction. So fluid, it is having all the three direction, but here we are simulating the actual phenomenon. So we will be assuming that fluid is having a streamline flow and it is coming out of inlet to the outlet along the x direction. So here we are selecting the x direction, and at this particular moment you have to give the value. Here I have already told you during y plus calculation I have given that I will be giving you 1 meter per second as a input velocity. So that 1 meter per second also should be given here, and v and w, that means your y direction and z direction, there will not be any kind of velocity because I am assuming that fluid will be only in the x direction, so I have to put it 0 0. So this particular value I have to give, and atmospheric pressure, it will be 0 atmospheric relative pressure, 0 we are considering. It is relative pressure, it is not absolute pressure. So there we are giving the 0 Pascal. So now apply, and rotating domain will be completely highlighted in the geometry, and then we will go for the next, that means the stationary domain. So stationary domain, so again we will go for the renaming. So because that is the rotating domain, this rotating domain already I have created, and now this default domain, another default domain. So I will start with the name first, then I will change its characteristics so that it will be fitting with the computation domain. So it will start with the initial defaults and then we will be changing these things. So here what will happen, again in the same manner, earlier I have selected B134, that name also has been generated by default. So but here we will be selecting B22. So B22 will be highlighting the part which belong to the computation domain. So it will be here, and fluid 1, this particular fluid 1, that particular value, that is already being water, because already we have selected water earlier, so it has been taken it by default. So water value, and then stationary, and see, in earlier we have selected rotating for the rotational domain, now we are selecting the stationary domain. So these changes you have to do, and pressure reference reference pressure 1 atmospheric pressure. So here stationary, and then fluid model. Fluid model is the heat transfer, whether any heat transfer, none. So and this one option SST, and then the turbulence, transitional turbulence, this is fully turbulent, and finally initiation will be the same, coordinate 0 Cartesian, and in the x direction 1 0 0, and relative pressure will be 0. So all these things we have considered, and now we have to generate the boundary conditions. So boundary condition, that means we have to give the boundary condition through this particular button. In rotating domain and in the stationary domain, if you bring it here, it will give you the two options, because already I have prepared two options. That is the reason I told you that you give the name properly, so that later on while you are selecting some other, through some other button, you should recognize. because so many components will be arising for similar type of thing. You have to give the name properly, otherwise you may be lost in the middle. So ultimately now we will be giving the boundary condition at the inlet and at the outlet. So in general boundary condition inlet, so here I am putting the inlet, I am giving the inlet name. So in the inlet name boundary condition, what will happening? So it is boundary type is the inlet boundary type, and again coordinate frame, 0 coordinate frame, that is there. Boundary detail, it is subsonic flow. Reynolds number, through the Reynolds number, if you try to calculate, so you will find out that Mach number will be less than 0.3. So ये subsonic flow है. Obviously ये subsonic flow है, supersonic तो है नहीं. So see subsonic flow we have seen normal speed, and then you can normal speed will be equal to 1 meter per second, whatever we have assumed earlier. Apply and OK. And then other options are also there, but we kept it default because there is no change was required which was given as a default. So I have not selected. If as per your problem, if something changes is required, so you can go with that. Now after that, initial boundary condition will be generated. If it's properly generated, so it will be highlighting here, as well as this arrow will be generating. So once this is generating, this black arrow, this will be automatically generating. After that we will go for the outlet. So outlet, again we will go with this boundary, and this new boundary that will be appearing. Obviously you can see that basically stationary domain, that is also being selected. So we are basically putting the boundary condition in the stationary domain. So in this manner we are giving the boundary to the stationary domain outlet. That was initially, that was inlet, this is the outlet now here, coordinate frame, and then boundary details. In the boundary details option, average static pressure we have given from 0.05, a few smaller value we have given here, and relative pressure it has been given as 0 Pascal. And then if you generate, then apply and OK, then it will be appearing as like this, that this is the inlet, this will be the outlet. So it will be appearing like this. And now you have to give the value for the wall. So the value for the wall, basically this particular computation domain, it is considered as the fluid itself. So the fluid which is placed inside the channel. So it is selecting the total part. So this wall, basically for this you have selected wall, and then location is the wall coordinate, and boundary details free slip wall. Here are conditions. You can say why we have selected free slip wall. There is no slip. We should have selected no slip wall, because free slip wall we are assuming that fluid will be passing over the solid surface without any intervention. No slip. With the wall and no slip wall, that means the fluid, whenever it will be interacting very near to the solid surface, there will not be any kind of velocity of the fluid. So basically in the simulation purpose here in this exercise, we have considered the free slip wall, so that we are allowing the fluid to slip over the solid surface without any intervention. So that particular option here I have selected here, and then the wall roughness we have considered as a smooth wall. So that is the reason we have selected is the free slip wall. So you can alter the options, and you can adopt different options for that, and you can see what is happening and which type of behavior it is showing in this fluidism. So now after that it will be looking like this. So the walls. Now we have to give the interface. Interface means now there is a rotating domain inside, and I have provided the boundary conditions here. What is happening inside here? Fluid which is coming through this computation domain, this is interacting with the rotating domain, and rotating domain have a rotational stationary frame, and this is having a stationary frame. So, and as well as fluid may interact here with this particular wall of this particular rotating domain. So this interface area we need to define. So for this, basically there is interface. So this interface, now we start giving the characteristics to this particular interface. So right click on this and insert the domain interface. So here the insert, right click, insert and domain interface. So domain interface, you can start with any name, and accordingly you will be selecting the surface. The way we will be selecting the name, the way the similar way we will be putting the characteristics. So here initially we have put the interface type is the fluid to fluid, because here also fluid, here also fluid. So interfacing is fluid to fluid, and now it is the stationary domain. Basically here we are putting the stationary domain here, and this is the part where basically we are considering the wall. So this particular wall, you can remember this names, this rotating domain S was provided for the wall of this. So earlier when we did the meshing, then we have put different parts, we have put the name of the different parts. So this name will be appearing here. So accordingly you will be selecting here. So this is the interface of the side 1, and this is the interface of the side 2. So accordingly you have to put the names here. So you can see the region list stationary domain, that is the SHRDS. S was for the stationary, and here SHRDS, this is for the rotating. So basically, see, now you can understand. So initially I have selected the stationary domain, this part, this wall part, the void part. Okay. Next while I am selecting the rotating domain, then what is happening? The rotating domain part also appearing. So it's the green one is a bit of thicker. So that means the simultaneous 2 it is being selected. So now this is the interface. This is the interface that we would like to define through the fluid interface. So and this is the transient rotor stator. That particular option will be frame change or mixing model is the transient rotor stator. So that particular option will be selecting. That is again those options we have selected through the literature, that for this type of case this particular option will be suitable. So now specific patch angle, you have to select specific patch angle. That means how it will be behaving, what is the movement here. So this movement is the 360 degree angle. So here we have to provide the 360 angle. So pitch, this pitch change, that will be 360. So total it will be rotating like this. So I have to give the 360 angle. That means stationary domain it will be remain here, and rotating domain it will be rotating like this. So how much? So 360 for one full rotation. So it may have some oscillation motion. So accordingly you have to give that. So here it is fully rotating. So it is 360 degree. So here after giving the 360 degree, now what is additional interface model? So conservative interface flux, and then you can keep these particular models because these are the defaults, and there is no such changes required actually here. And mesh connection will be GGI. So this particular if you put it here, and then we will go for the another part. So inlet of the rotating domain from the stationary domain. So inlet part we will be doing. So here insert domain interface, and domain interface 2 it is, and we are not changing here this domain interface name. So you can give the name, you can keep it like this. So here domain interface 2 we are keeping. Again all are the fluid interface. So fluid is coming here, here also fluid. So fluid interface, and again first one is the interface side 1. This is the stationary domain, and stationary domain inlet, we are talking about the inlet part. So that is why SHRDIN. In this manner we have given the name. So the inlet, and here this is also inlet, but SHRD inlet different. SHRD SIN stationary domain, for stationary domain that was given as SIN. S symbol we have used. I cannot provide bigger size of name, it may have problems, so you have put a smaller name. So SHRD in, only in, so that is representing actually inlet of the rotational domain. So you can see, you can just check this particular part. So here it has been again highlighted thicker. So just check first one and the second one. So now interface has been defined. So again similar options, specific patch angle 360 degree because total system is rotating in 360, and GGI. So now third one, outlet. So here we will go for the outlet. So outlet, first one will be stationary domain and set SHRD S out. S means stationary domain, that out. So that out, that has been already selected. Now next one. So okay. So next one actually initially this one, now it has been highlighted more, but actually it is not that much visible anyway. So the same way we have selected. Now the option, rest of the options will be remaining same, and now the thing is we have to define the interface here inside for the solid. So here again we are putting the name here as a rotor. So now the basic is the wall, and then no slip wall. So there will not be any slip. So it is assumed that fluid is coming and it will be interacting the solid surface, and then it will be moving. So now here sources will be applied, and then it will be generated. Now next of the thing is transient blade row model. I have already mentioned that for this particular analysis we will be using transient blade row model for the turbo machines part. So this transient blade row model, this particular model parameter also I need to define. So here if we double click on it, so what is the basic setting? Basic setting, time integration, it is important. So this time integration, and then the passing period, you have to define the passing period, and then here say for this particular setup actually I am trying to replicate if 100 RPM is given to this particular turbine. Given means say fluid velocity is 1 meter per second, and if it is rotating with 100 RPM. So what will happen? How to simulate those things? Now you can say what is the guarantee of rotating of the 100 RPM? Because of the load. That means we have already discussed about the load. That is the load which is the electricity load. We are basically simulating electricity load through the mechanical load, and if we increase the mechanical load, its speed will be reduced. If we decrease the mechanical load, its speed will be increased. Say we have fixed that this particular turbine, if it is rotate at 100 RPM for a certain amount of the load. Here load we are not defining, rather in the reverse way we are defining the rotation, because that giving that particular value to the software is easier. So here if we are telling that fine that 100 RPM we are 100 time step we are basically giving. So given speed is 100 RPM, that means one revolution will take 1/100 minute. One revolution will take, this is the calculation you need to remember. Means you have to understand accordingly, you have to put the value here. Here I have put here 100 and I have put here 0.006. From where it is I am getting this value. 100 you can give, that is user defined. For this particular case I am defining the 100. For another case I can go for the 60 RPM. Say we are discussing about the 100 RPM case. So 100 RPM case, that means rotation per minute, 1 minute 100 rotation. So what will happen? One rotation will take 1/100 minute. So that means that much of second. Okay. Now one revolution equal to 360 degree. One revolution equal to 360 degree, and 360 degree equivalent to 100 step. So one time step it will be equal to 360 divided by 100, that means 3.6 degree. Okay? So this 3.6 degree, basically this actually from this we can find out that 60 divided by 100, that much of second equal to one revolution. So 1 degree will be equal to 60 divided by 100 multiplied by 360. So 3.6 degree basically require how much of second? It will give you equal to 0.006 second. So one time step require 006 second. So in this manner, if you are selecting here 100 instead of 100, if you are selecting 60, so you put 60 here and you come up with 0.01 second. Same calculation. So accordingly you have to give here it is 0.00999, that means 0.01. So accordingly you have to give the value. Another thing is how many number of rotation you need to calculate. The calculation here I have provided for the one full rotation. One full rotation. So such type of rotation, how many rotation you would like to give? So I say I would like to give 4 rotations. So that means the value will be calculated for the 4 rotation. Now you have to decide whether you will be calculating for the 4 rotation or you will be calculating for the 10 rotation or 20 rotation. Based on the size of your model, based on the mesh or element generated, based on the capacity of the computer, then you have to select that how many number of the period of run you will be doing, and that where you will be saving the data, which data will be saving. So accordingly, what will be the means size of the file in terms of the GB, it will be stored, whether that much amount, that much time, how much time will be required to complete the exercise. All things actually depends while you are selecting those particular parameters. So that you will understand corresponding to your problem while you will be doing the exercise for a few times. Then you will understand. So here I have given you some example that okay fine, if I do this type of thing, so what will happen? So apply OK, and then transient blade roll models, that particular part is over. And now what will happen? So solution unit, now solver control. After that the solver control will be there. So double click on this, the basic setting will come. So basic setting you have to give for the high resolution, turbulent numerics, high resolution, and this values basically you have to increase here more than 10. Means here I have selected it 10 because I wanted to complete the exercise so that I can take out the this screenshot, I can make I can prepare the presentation. Otherwise I could have given more for actual calculation. So now you have to define the convergence limit, your calculation convergence limit. The lesser will be the value, it will be better, but it will again take the more time. So you have to tune it. So here 10 to the power minus 5, that value I have given for the conversion. Now there are different equation class setting is there. Continuity equation, momentum equation, turbulent eddy frequency, turbulent kinetic energy, all the things I have put the reasons of considering all these things, the different. So 1, 2, 3, 4 options I have given you. If you would like to select any one of these options, how to select. So now after that basically you have to select the reach out option. This particular option here also, why it is selected, this is collocated grid is actually selected. This collocated grid and staggered grid, two type of grid actually being formed while it is doing calculation, and this collocated grid is actually done for the complex geometry and multiplex flow, all these things. So it is suitable for our analysis. So we have selected this reach option and then ultimately you will be applying an OK. So after that you have to almost all the setting has been completed, but now I have to define actual calculation. That means I have provided the rotation. From the rotation basically it should give me the calculation of the power. So that particular exercise I need to complete. So calculation of the power, that will be given by the expression. So this expression basically you can give, you double click on this, you can give insert expression. So insert expression, so what will happen, one expression will come. So this particular expression you can define as a name, you can name as a n, expression name, and this n, if it is you are trying to define it for the RPM. So here you will be giving the value 100 RPM. For our case this is 100 RPM, and then you can add more expression. So another expression, suppose I am trying to find out the torque at the x-axis. So torque at the x-axis, if I would torque at x, y, z different axis may happen in case of other geometry. For our case it will be torque at the x-axis. So x-axis was like this and turbine was rotating like this. So torque at the x-axis. So torque at the x-axis I have given name as torque x. So accordingly here I have defined the torque at the x-axis, and these symbols, this is the notation. You have to add a rotor. Rotor I have given the name because I have defined this as a rotor. My name was rotor. Initially I have given the name of the interface as a rotor. So accordingly I have selected it there, or you can find out the option, these values. function locator based and torque. In this manner also you can find out, or you can use the syntax. So which torque you require? Torque at the rotor at x-axis, about the x-axis. So you have to select it like this. Now torque is given like this. Now I want to calculate the power. So power is equal to torque multiplied by omega. N is there, so N will be giving you the omega, and then torque multiplied by torque, it will be giving you the power. So that particular expression I can find out. Torque will be here. Basically I will be writing expression torque is equal to torque will be rotor, and then torque x, because that is torque s, multiplied by, this is pi, multiplied by n divided by 60. Simple torque equation. So that will be completing, and you have to apply. Then whenever we will be running this particular software, it will give you the value. So this is now parameter of the output control that is being completed. This output control, that will be standard, and this transient result, this option transient result, and then output frequency, that means which data you basically control through the output, which data you require to be stored, that will be, you can extract, and or that will be used for generation of the graphs. So that also you have to define. If you select more number of data, that means denser data interval, so your file size will be huge. So after a few running, you will understand what should be the interval of selecting the data. So anyway, so that every time step here, because I have made it course, so every time step I would like to solve. I would like to calculate and save. So that is there. And monitoring purpose, so monitoring is there, you can select it here, click it on, and then monitor point 1, and this monitor point actually will show you the graphs later, it will contribute there. Expression, and this expression will be, we found out through the expressions already we have created. N expression is there, torque expression there, power expression there. So those expressions will be there. And monitor 2, so we can use another expression. So here we are using torque and apply OK. So two monitors we have generated, and finally save and exit. So now we will run this. So whenever we will run this, it will take, just I told you, it may take 1 day, 2 day time. So so after that it will run, and you can save your project with this name, WBPJ format, and finally then you can run. It will be looking like this. And whenever you will be running, so there is an option whether you would like to run it to parallel or serial competition. So here we have used the serial one, so options will be there. And when you will be running, you can see momentum and mass versus time step. So turbulence versus time step. So wall boundary versus time step. So this type of, and in the right side, so different convergence history it will be giving you, and it will keep on producing the results. So this particular results will be used, and here ultimately this type of graphs will be created. So these are the RMS value, convergence criteria we have considered, that particular values will be there in, U direction, V and W direction. And finally this turbulent result, that particular values are there. One is turbulent K epsilon value and turbulent frequency value, that is given, and wall boundary conditions, that is also given. And here basically we have got monitor point 1. Monitor point 1, what we have considered, I think power, or anyway power, we have two monitor point, one was power and one was torque. So here basically we are, I have written it here. So monitor point 1 is the power x, and monitor point 2 is the torque x. So these two value, that means monitor power 1, that means red one. So red one giving me the power, and this one is giving me the torque. So now the value we are getting, basically this fluctuation we will try to avoid, we will try to get the this stabilized value. So this is the value basically we will consider as our output for this particular accumulated time step. Or you can save this particular, you can find out this value from the CSV file which has been stored. Okay, so save the result. You can save the picture also, or you can save it in PNG format, or you can save it in comma separated values CSV format, and then it will be looking like CSV format will be looking like this, or PNG value it will be looking like this. Okay, so I will show you video of this. Ek minute. I will show you the video. This particular video, how it will look like. Let's see, this is the video. How much? 4-minute video. So you can see. So far whatever we have discussed, how it will be looking like. So while opening it is in 10x speed, it is taking so much of time. So that is the reason we made it earlier. This slide, and I hope this is the video. I hope slides will also work. Yes. That will be useful. Slides in PDF format I will give you later. All the slides. These are the expressions. Output control. Finally done. So you will be generating like this value. You can see coefficient of loop iterations, so different iterations is showing. All the CSV values, CSV calculation values are there.